Okay, now another version of a frequency distribution is what we call a relative frequency distribution. And these are probably quite common. And instead of using the actual frequencies, what we do is we use the relative frequency, or the decimal equivalent of a percent. So what's the proportion that fell in each category? This is useful because it allows us to compare data sets that maybe don't have the exact same total number of values in there. So if I were looking at this as a frequency distribution, and I said from school A, our 400 meter times, there were 2 people that ran 55 to 64, 6 people that ran 65 to 74, and I said from school B, maybe there were 8 people that ran in this category and 10 people that ran here, and so on and so forth. Well, it would be really hard to do a comparison as to like which school was maybe considered better, because my guess is that there's probably a lot more people at this second school since the values are higher. So just comparing 8 to 2 doesn't give us the whole picture. But what we can do is we can put them into relative frequencies, and that levels the playing fields. So to do this, what we need to do is we need to find the total number of observations in our data set. So to do that, I would add my frequencies together for this first data set here. And it looks like I have 22 total participants in this table. Now to do my relative frequency, I would take 2 divided by 22. So the 2 comes from my frequency here. The 22 is my total. And then I would divide that out. And that would give me my relative frequency, 0.09. Then for my next one, I would take the 6. So there were 6 people in that category. I would divide that by the 22. And then that's going to give me 0.27. I would do that for each of these categories. And that's going to give me my relative frequency for every single one of them. Now, if we think of this as percents, this is like 9%, 27%, 36%, 18%, and then 9% again. So these are the decimal equivalents of the percents. Now, when we are doing relative frequencies, this should add up to 1, because if we included everybody, that would be 100% of our people. So the decimal equivalent of 100% is 1. Well, when I add these together, this only turns out to be 0.99. Now, the reason that that occurs in this example is due to rounding. I rounded each one of those values. So the rounding error shows up right here when I find my total. That's going to be pretty common when you're doing relative frequencies if you use rounded values. So as long as you're really, really close to 1.00 for your grand total in your relative frequency column, then you've probably done it right. If you're a little ways off, like if we had gotten 0.95, then I probably made an error somewhere up here, and I would want to go back and double check my work. Now, from a relative frequency table, we can produce a cumulative frequency distribution. If you think of what cumulative means, it means added up as you go along. So what this does is it's going to show the sum of the frequencies for the classes in all previous classes. Now, when we do a cumulative frequency distribution, the category name is slightly different. So we're not just going to leave them as 55 to 64, 65 to 74, 75 to 84, and so on, because we're going to be looking at everything at that level and previously. So most of the time they will use the terms like less than 64, and here we would have less than 74 and less than 84 for our categories. So to do our cumulative frequency table here, if I look at my original table here, the number of items that were less than 64 is just those first 2. But now the number of items that were less than 74, well, I have these 6 right here and these 2. So I'm going to take those and add them together. That's where the term cumulative comes into play. Less than 84, well, I'm going to take the 8 plus all the categories that I had before that. So that would be 16. And then less than 94, I need to take 4 in all the previous categories. And then less than 104, I need to take all of the categories that were before that, which brings me up to a total of 22. Now notice this last value here was the exact same that we found on the previous page when we did our relative frequency and we had to add all these together. Because at this point, less than 104 should be everybody that I had, so it should be all 22 individuals. We can also do cumulative relative frequency distributions. So if we bring our relative frequency values back from the previous page where we calculated those, and we turn that into a cumulative relative frequency distribution, I would do the same thing. I would have 0.09 for my category of less than 64, and then when I do less than 74, I would add those two values together, get 0.36. And then when I do less than 84, I would have all of those values together, 0.72. In my next category, I would put the 18 in there, 0.90. And then again, we can see our total here, that 0.99 that we found before, that technically should be 1.0, but we have a rounding error in there. So we can do cumulative frequencies, and we can also do cumulative relative frequencies. Now, a lot of times we are going to use frequency distributions as just the very beginning of when we start to explore our data sets. Now, one of the things that we will sometimes look for is whether or not our data seems to represent what's known as a normal distribution. Now, a normal distribution from a graphical point is represented by that type of a graph. So we start out low, we go high, and we peak right in the middle, and then we decrease back to low. So an example would be this frequency distribution right here. We start out low, 2, 4, and we're increasing as we go. And right when we get about to the center, we peak, and then we start to decrease as we go again. So this frequency table, we could say, might represent a normal distribution. Now, there are other things that we would look into to see if it actually does represent a normal distribution, but this is just kind of a starting point. Okay, another thing that we can sometimes try to figure out is determining, was our data measured or was it likely self-reported? So let's say we're doing these pulse rates here. And as we look at our frequency distribution, we notice that there's this kind of a strange pattern. This is the last digit of the pulse rate. So if you had a pulse rate of 65, you would have been in this category because the last digit of 65 is a 5. And it says 0 people reported that, but 31, maybe reported 64, and 28 reported 66. So it doesn't really seem logical that there would be 0 for that particular category. So more than likely what happened here was that they probably didn't measure the heart rate for the full minute, but they probably measured it for 30 seconds and then just doubled that value, because notice all of our frequencies have an even value for their last digit. Okay, another thing that we can sometimes see are gaps. Okay, so here we have a frequency distribution from a sample of pennies, and the mass of the pennies represents our classes that we have over here, and these are in grams. And then we have our frequency. Now notice we have a great big gap here. We have 3 consecutive categories that have 0. And we have a significant number of frequencies below that gap and above that gap. So what that can do is that can possibly give us an idea that, maybe something was going on here. Well, with pennies in 1983, they changed the composition of the pennies. They used some different metals in them. So this right here are probably pennies that were either made before or after 1983. And then this down here would be the other group. So that gives us a visual representation. That would have been very hard to see from just a list of data sets. But when we put it in the frequency table, we can see that gap there, and then we can start looking into why is it possible that might have happened. Okay, and then one other thing that frequency tables often let us do is it often lets us compare data sets. Now, when we're doing the comparison of data sets, it is definitely recommended that we use relative frequencies, like I had mentioned before, because if our sample sizes are not the same size, it's very hard to compare just straight frequencies. So here I have a comparison of males to females. Let's say that this is the amount of time spent watching TV or something like that. And we have 0 up to 1 hour, 1 up to 2 hours, so on and so forth. So we can do a comparison now of the males to females, put them in a side-by-side table here, and we can try to look for any patterns, similarities, or differences. So relative frequencies are usually just the very first step when we talk about exploring data. They kind of give us just that first snapshot of what might be going on and what are some other things that we should be looking for.